Hello and welcome to my video on buffer solutions. Hope you guys are all having a good day today, or whatever time of day. If it's night time, hopefully you've had a good night. Today we're talking about buffer solutions in the HSC chemistry topic of acid-base reactions. So what actually is a buffer? Well, a buffer is a solution of weak acid or base which is occurring in an equilibrium, which is often used to calibrate pieces of laboratory equipment such as pH meters or pH probes. They can also act as a standard in the sense that they have an exact pH range due to their equilibrium nature. The two main examples of buffer solutions that we see in our topic of acid-base reactions is the acidic buffer of acetic acid and the basic buffer of ammonia. The reason why these chemicals are used as a prominent example of buffer solutions is because they both have a low degree of dissociation, which essentially means that they don't dissociate in water. Well, they do dissociate, but at a very low percentage. We will come back to this later on in the video. It should be noted that both of these systems have to be in water for the equilibrium to be in effect. So now let's dig deeper into what is actually happening in the equilibrium system. So here we have acetic acid and water in the system, and what happens is the acetic acid molecule CH3COOH will lose one hydrogen to form a hydronium ion with the water molecule. So now we have our equilibrium established. Because acetic acid is a weak acid, it means that only a certain percentage of it will dissolve, but there will still be acetic acid molecules left over in the solution. Therefore, if any of the products are taken away, so if any acetate ions or hydronium ions are taken away, they will simply be replaced by the excess of acetic acid molecules in the solution. For example, if another acid is added, say if we add hydrochloric acid, we'll be adding more H plus ions, or hydronium ions rather, and this will affect the equilibrium because we are adding products. And according to Le Chatelier's principle, if we add a product to a system in equilibrium, it will shift the whole equilibrium system to the left, favoring the reactants. So in effect, the added H plus ions will just remove some of the H plus that is already in the solution from the acetic acid and reform into the CH3COOH. On the other hand, if a base is added, some of the H plus ions will be removed from the solution and neutralized to form water molecules. And again, according to Le Chatelier's principle, if we take away some of the products, some more of our reactants will turn into products, meaning that more of our acetic acid will dissociate to replace the H plus ions that are lost in neutralization. A similar phenomenon occurs with a solution of ammonia. Ammonia in water allows the ammonium ion and hydroxide ions to form in an equilibrium as shown. In this reaction, if more hydroxide ions are added, then they will simply be taken away and formed back into water and ammonia. So we know what happens to the basic buffer solution if we are adding hydroxide ions to it, but what happens if we add hydrogen ions to it? Well, we will be removing some of the product, therefore shifting the system to favor products. And what this means is that more of the ammonia and water will dissociate into more ammonium ions, but rather we want more hydroxide ions. And this is what negates any extra H plus ions. The features just described of the buffer solutions is what gives it a pH range rather than just a single pH. We have a range of pHs which we know that our buffer solution will be solid for. We know it will be an exact value between a set of values. In this case, I won't actually explain what those values are, what those pH ranges are, but all you need to know is that these solutions cover a range of pHs due to their ability to absorb H plus and hydroxide ions. Now, what would happen if we kept on adding, say, hydroxide ions into our acetic acid buffer solution? Well, eventually all of our acetic acid molecules would be used up, and then the solution would end up going to acidic conditions, or rather basic conditions. The same thing would happen if we kept adding H plus ions or acid to our basic buffer solution. Eventually all our OH minus hydroxide ions will be used up, and then our buffer solution won't be able to resist any extra hydrogen ions, therefore lowering the pH. So as described earlier in the video, buffer solutions rely on weak acids and weak bases. And when we talk about weak acids and bases, we talk about dissociation, and weak meaning a low dissociation. Now, if we have a solution with a weak acid or base, in this case, we just are using the general formula of HA and BOH, we'll end up with a strong conjugate acid or base, depending on whether if we started with a weak acid or a weak base. Now, the conjugate part of this equilibrium system doesn't really affect our reaction, but we really need to focus on the weak acid and weak base part, and remember that the reason why we use weak acids and weak bases is because of the fact that they have low dissociation. The low dissociation is what gives buffers their ability to essentially eat up any extra hydrogen and hydroxide ions that are added to solution, because there would be more of our reactants to fill the empty space of any products taken away, or added for that matter. Anyways, that should be the basics of buffer systems, and if you can remember that buffer systems use weak acids and weak bases, and remember that acetic acid is a common acidic buffer, and that ammonia solutions is a common basic buffer, you should be alright understanding the concept of buffer solutions. Thank you for watching, and please like and subscribe. If you made it this long in the video, I thank you very much, and here's your daily explosion. Let's get it. Get back.